Tunnel diode. Introduction to tunnel diode. Tunnel diode was invented in 1958 by Leo Esaki. Leo Esaki observed that a semiconductor diode is heavily doped with impurities. It will exhibit negative resistance. Basically, it is a heavily doped p-n junction. These diodes are fabricated from germanium, gallium arsenide gas, and gallium antimonite. Definition: tunnel diode is a semiconductor with a special characteristic of negative resistance. By negative resistance, we mean that when voltage increases, the current decreases. Highly doped p-n junction. Tunnel diode has doping density of about 1,000 times greater than ordinary junctioned diode. Symbol: in a tunnel diode, the p-type semiconductor acts as an anode, and the n-type act as a cathode. We know that an anode is a positively charged electrode that attracts electrons, whereas a cathode is a negatively charged electrode that emits electrons. In a tunnel diode, an n-type semiconductor emits or produces electrons, so it is referred to as the cathode. On the other hand, a p-type semiconductor attracts electrons emitted from the n-type semiconductor, so a p-type semiconductor is referred to as the anode. Construction. Starting material. The starting material for a tunnel diode is typically a single crystal of silicon or germanium. Doping. The crystal is doped with impurities to create two regions of different conductivity. One region is heavily doped with impurities to create an n-type semiconductor, while the other region is heavily doped with impurities to create p-type semiconductor. Junction formation. The two regions are brought into contact to form a p-n junction. The junction is typically formed by diffusing one type of dopant into the other region. Thin barrier layer. In a tunnel diode, the p-n junction is designed to have a thin barrier layer. This layer is created by using a specific doping profile to create a narrow depletion region at the junction. Contacts. Metal contacts are added to the semiconductor material to allow for electrical connections. How does a tunnel diode works? 1. Unbiased tunnel diode. When no voltage is applied to the tunnel diode, it is said to be an unbiased tunnel diode. In the tunnel diode, the conduction band of the n-type material overlaps with the valence band of the p-type material because of the heavy doping. Because of this overlapping, the conduction band electrons at the n side and valence band holes at the p side are nearly at the same energy level, so when the temperature increases, some electrons tunnel from the conduction band of the n region to the valence band of the p region. Because of this overlapping, the conduction band electrons at the n side and valence band holes at the p side are nearly at the same energy level, so when the temperature increases, some electrons tunnel from the conduction band of the n region to the valence band of the p region in a similar way. However, the net current flow will be 0 because an equal number of charge carriers, free electrons, and holes flow in opposite directions. 2. Small voltage applied to the tunnel diode. When a small voltage is applied to the tunnel diode, which is less than the built-in voltage of the depletion layer, no forward current flows through the junction. However, a small number of electrons in the conduction band of the n region will tunnel to the empty states of the valence band in the p region. This will create a small forward bias tunnel current. Thus, tunnel current starts flowing with a small application of voltage. 3. Applied voltage is slightly increased. When the voltage applied to the tunnel diode is slightly increased, a large number of free electrons at the n side and holes at the p side are generated. Because of the increase in voltage, the overlapping of the conduction band and valence band is increased. In simple words, the energy level of an n-side conduction band becomes exactly equal to the energy level of a p-side valence band. As a result, maximum tunnel current flows. 4. Applied voltage is further increased. If the applied voltage is further increased, a slight misalign of the conduction band and valence band takes place. Since the conduction band of the N-type material and the valence band of the P-type material still overlap, the electrons tunnel from the conduction band of the N region to the valence band of the P region and cause a small current flow. Thus, the tunneling current starts decreasing. 5. Applied voltage is largely increased. If the applied voltage is largely increased, the tunneling current drops to 0. At this point, the conduction band and valence band no longer overlap, and the tunnel diode operates in the same manner as a normal p-n junction diode. If this applied voltage is greater than the built-in potential of the depletion layer, the regular forward current starts flowing through the tunnel diode. The portion of the curve in which current decreases as the voltage increases is the negative resistance region of the tunnel diode. The negative resistance region is the most important and most widely used characteristic of the tunnel diode. Characteristics: the p-side's Fermi level rises above the n-side's Fermi level when reverse bias is applied. Consequently, electrons move through a tunneling process from the balancing band of the p-side to the conduction band of the n-side. The tunnel current likewise rises with the introduction of the reverse bias. When forward bias is applied, the n-side's Fermi level rises above the p-side's Fermi level, causing electrons to tunnel from the n-side to the p-side. The tunnel current is much larger than the typical junction current in terms of quantity. The tunnel current increases up to a specific point. When the forward bias is raised, the tunnel current is at its highest. When the band edge of the n-side matches the Fermi level in the p-side, as the forward bias is increased, the tunnel current declines and the desired negative conduction area is obtained. Normal p-n junction current, which is exponentially proportional to the applied voltage, is obtained as the forward bias is raised further. The VI characteristics of the tunnel diode is: the negative resistance is used to achieve oscillation, and often CK plus function is of very high frequencies. Advantages and disadvantages. Advantages: long life, high-speed operation, low noise, low power consumption. Disadvantage: tunnel diodes cannot be fabricated in large numbers. Being a two-terminal device, the input and output are not isolated from one another. Applications: tunnel diodes are used as logic memory storage devices. Tunnel diodes are used in FM receiver. They are widely used in satellite communication satellite equipment. Thank you.